This time on the channel, I do RF origami. So the start of this is I needed a 2-meter antenna. Granted, I could have just went out and bought something commercial, but hey, what's the fun in that? Enter the Astroplane. The Astroplane was a CB antenna made back in the 70s, and my bright idea was, hey, could I downsize or scale down the Astroplane, which was originally a 27 megahertz antenna, and make it work on 146 megahertz? And what follows is me actually doing that. So one of the things you can do when you're building antennas is to model it in some sort of a software program. In this case, I'm using EasyNEC, and I just threw together a quick, crude model of an Astroplane tuned to 146 megahertz just to see what the elevation radiation angle would be. When you do an elevation plot, you can see it's pretty good with this antenna. At 6 degrees, we got 4.83 dBi gain. That's not too shabby. We always like it to be a low angle. Since I live in a mountainous area, I would like the gain to be acceptable at a little bit higher angle, just in case I'm trying to communicate with somebody that's up on the side of the mountain. So you can see that as you go up in radiation angle, it's still pretty good. At 28 degrees, we got 2.47 dBi. So there is still some gain, even up at a higher angle, but down around 6 degrees, it's absolutely beautiful. But I wanted this antenna to also be resonant on GMRS frequencies, which is 465-ish megahertz. And we do a plot there, things change. And you can see that it's just absolutely horrendous. Now, the SWR at 465 megahertz is pretty good, but the radiation angle is just horrible. I mean, it's just simply not going to work. This thing's a cloud burner. So you get down into low angle radiation where the antenna would be the most useful, and you can see we have negative gain. In this case, negative 6.19, and even lower yet, negative 4.87 dBi, so pretty much useless at low angle. That's why I like to model things to see how they're going to radiate. So although this one would work fine on 2 meters, it's not going to be an acceptable GMRS antenna. So here's my mast. It's just a piece of aluminum that I had laying around. Not sure what it came off of, but it's thin wall. It should be enough for this little tiny antenna. There's a little dent here at the top. But that's not going to hurt anything because I'm going to cover it up with this bracket right here. So this is just a piece of aluminum that I've cut and put some slots in it. It's a C-channel. And I'm just going to attach it to the mast with hose clamps, or a hose clamp, like so, through there. And then when I go to attach the copper to the bracket, I've got some heat shrink to isolate the driven element. And then the other one will just be hose clamped straight to our little bracket here. So this should work okay. One of the unknowns is the width of this bracket. And I'm not sure if the width of this bracket is critical as far as matching goes. So we're going to find that out. I reasoned that since 2 meter everything is shorter, that the bracket would also be shorter as well, but that's just a guess, so we'll find out. So going from 27 megahertz down or up to 146 megahertz is about a factor of 5. So everything is about 5 times shorter than it would be on a 27 megahertz antenna. So I did the math on all the measurements. Luckily there were measurements that I could dig up on the internet, and I've got them right here. And I'm going to start with the hoop. And when you scale the hoop to 2 meters, I got about 5.5 inches diameter for the hoop. I'm going to leave 2 inches of overlap just in case I have to make that a little bit bigger. So we're going to cut this piece of wire. We're just going to use pi. So you take 5.48 times 3.14 and you get 17.22 inches for circumference of the hoop. And I'm going to add 2 inches of that. So here's our copper. This is just ordinary bare copper that you can get from the hardware store. This was about $9 worth of copper. And okay, 17.22 is what I've got for measurement, so I'm going to make this 19, let's make it 19 and a half. So I'm going to cut it right out there. And then we just need to form this into a circle. Now if I'm lucky, I can find something that's about 5 inches in diameter, which would be the best way to do this, and just wrap it around it. So this is about 5 inches, but I'm going to use it for the form, and then I can relax it after that. That's about right. Right about like that. I'm betting that this will be about the hardest part of doing this. And I'm also not going to use a soldering iron for this. I don't think it would get hot enough. So I'm going to be using a butane torch. Whoa, it's still warm. Okay, the hoop is done. I'll keep that heat sink here. I think I'm going to need it. Okay, on to my next measurement, which is our bottom wires. Let's see, these are called out A, B, C, D, E, and we're going to do, let's do B, D, and A. I can combine as one wire. So 25, 29, if I add up A, B, and D. And I do need a little extra because at the top I'm going to have to bend the copper to make a platform to solder the capacitance head on. And at the bottom, of course, we're going to have to overlap it slightly. Very little bit, 1/4 of an inch maybe. So we'll make it, let's see, extra inch at the top. So we'll make it 26 and a half. Alright, this one does have to be straight, so I'm going to try and straighten it out as best I can. I have not built the spreader yet. That just needs to be something that is not a conductor. I'll probably use a small piece of PVC tubing. Alright, that's probably good enough. And what I'm going to do is I'm going to solder them away from the part that I just soldered. Hopefully I won't disturb that one. Okay, next wire is going to be C and E, and C is 8.7, so 16.8 plus the overlap. And the overlap is only what goes below the hoop or attaches to the hoop, and then what goes up into the insulator where it's going to be fed. So actually, yeah, it's going to be the width of this piece will be the overlap plus 1/4 of an inch. So this is 1.5 inches, well, I 1/4 inch that, so 1 3/4 will make it 18.5. Or just a scoosh more. So when going from 27 megahertz up to 146 megahertz, it's not going to be a direct scale because of end effect. And end effect is due to the diameter of the wire. So the bigger the wire, the more end effect you get. And it's basically like a mini capacitance hat because of the diameter of the wire. So if you could use a very, very, very thin piece of wire, you could avoid the end effects and the scaling would be exact. But then your antenna wouldn't be very broadbanded and there would be other issues as well. So I'm not going to set it up that way. I'm just going to use this copper, which will work just fine. Theoretically, it should be shorter than what I calculated, but I don't know. We're breaking new ground here, so we'll see. I don't want to undo what I've already done. Get a nice big ball of solder in there. So a soldering iron wouldn't work for this unless you have a really, really powerful one, because the tendency is that the copper wants to wick the heat away. And there's the start of our antenna. So now we need to put the bracket on it. And the way that I'm going to do that is I'm going to measure up. Let's see if I can figure out where the bracket is supposed to be. So C and E was 8.7 and 8.1. 8.7 plus 8.1 equals, so 16.8 inches up. Roughly you're at about there. And then, of course, this will be the same, 16.8. Right about there. So if this works, I might have to actually invest in some silver solder. See if I can get in and out real quick on this. Well, my hoop is a little crooked. Let's see if I can, yeah, I can pull it up just like that. All right, this is not going to be easy. Somehow I have to hold all this up there and solder it in place. About like that. I think I'll tie it with some copper wire. Here's the finished product. I had to move the feed point slightly. When I first put it together, the SWR was just atrocious. So I moved the feed point down a little bit and I shortened it just a hair. And we're actually pretty close. It showing that it's 1.6 to 1 at 132 megahertz. So I'm going to play with the elements a little bit and see if I can get it down below that. Got it down to 1.1, and I did that by spreading the elements a little bit. So you can see those are spread out a little bit wider. I think that's what this wants. I think that bracket might need to be a little bit wider, but it is going to tune out right here, I think. This is the finished product. I had to trim it quite a bit to get it to resonate. I actually ended up trimming the capacity hat almost all the way off, which in a way makes sense because end effect is much more prominent on higher frequencies, so it really didn't need it. The thickness of the wire was enough. So I've got that cap hat down to a 2.5 inch cross of copper, and the rest of it's like so. Now, one thing I've noticed on this antenna already, you'll notice as my hand gets close to the coax, it starts changing. So this thing is loaded with common mode current. And I'm going to see if I can fix that right now. So that build video is about a year old, and what I mentioned about common mode current you can fix by just doing kind of an ugly balun, and it's just 4 or 5 turns of coax in about a 5-inch circle, and that will usually take care of it at UHF and VHF. So anyway, this antenna has been up for, like I said, about a year, and it's been a great antenna. It's working fabulously. The SWR is still good on it. Signal's good enough. I'm sure there are better VHF antennas that you could buy commercially that would have more gain than this, but this antenna hits the local repeater with no problems, and it's about 40 miles in that direction, up on that mountain way out there. You can barely see it on the horizon there. So about a 40-mile trip as the crow flies. That does pretty good. So pretty neat little antenna. I'm very happy with the way it turned out. So there you have it. I hope you enjoyed that build video. Thanks for watching.